This video is on Chapter 9, Section 9.7, Common Acid-Base Reactions. So there are two types of reactions we'll go over, and the first type is the reaction of acids with dihydroxide bases. You remember maybe we have already talked about the neutralization reactions, and at the time you learned that an acid and a base give a water and a salt when they react together. And this is called a neutralization reaction because the acid neutralizes the base and the base neutralizes the acid. And you can see that because we are forming water, which is a neutral substance. So neutralization reaction is an acid-base reaction that produces a salt and water as products. If we write a general form of that, HA will represent the acid because we need a formula where H is first in the formula to say that it's an acid. The base, we will use those strong bases that are made of the hydroxide ion. Remember that the hydroxide ion makes strong bases. And so M here represents a metal from group 1A or 2A, the alkali metal, group 1A, or the alkaline earth metals from group 2A. These metals usually make a compound with the hydroxide ion, and these compounds are basic. So if we put them in solutions, in aqueous solutions, and make them react, it's still the same principle for an acid-base reaction where the acid donates a proton to the base. And so here the acid will donate an H plus to the base. The base, which is represented by OH minus here, will accept that proton. And we know already that H plus, when it binds to OH minus, they make H2O, right? The positive charge from the H plus and the negative charge from the OH minus cancel. And now we have two H's and one oxygen. And that's the formula of water. Next, the cation from the base, because that's a positive ion, the M, that is combined with OH minus, will combine with the negative ion that comes from the acid. Because when the acid donates a proton, it leaves behind A minus. So M plus SA minus combine together to form the salt that will have the formula Ma. We always put the positive ion first in the formula and then the negative ion. And so that's how an acid-base reaction forms water and a salt. So let's look at an example of a neutralization reaction. For example, write the balanced equation for the reaction of MgOH 2 times with HCl. So MgOH 2 times and HCl are your reactant. And out of these two reactants, you need to identify the acid and the base. So the one that has hydrogen first in the formula is the acid. So HCl is our acid. And then MgOH 2 times is the base, because you can recognize in that formula there is the hydroxide ion OH minus. So you write them on the reactant side, and you write water as a product on the right side of the arrow. We have water as a product because the H plus from HCl will combine with the OH minus from MgOH 2 times, and H plus OH minus make water. Now we need to find the formula of the salt. And so we already know that from HCl, we have H plus, which already reacted with OH minus that comes from the base, and together they form water. So what's left is the chloride ion, Cl minus, that came from HCl, and the magnesium ion that comes from the base, MgOH 2 times. Mg magnesium is a group 2A metal, an alkaline earth metal. So group 2A, so it's a 2+ ion. And chloride is a -1 ion. So you place them next to each other by writing first the cation and then the anion. And when you place them in that order, you can do the crisscross trick, and you see that the 2 from the Mg2+ will become subscript for Cl, and then the 1 from the negative charge of Cl becomes a 1 for magnesium, which is implied, and we don't write that 1. So the formula is MgCl2. So you can add that on the side of the product. And we have HCl plus MgOH 2 times gives water plus MgCl2. The last step is to balance the equation. We can see we have magnesium 1 on each side. However, we have 2 chloride on the right and 1 chloride on the left. Another thing that is makes it easy to balance this type of reaction is to notice that you have 2 hydroxide ions in the base, but only 1 H+ in the acid. And each H+ needs to react with 1 OH-. So if you have 2 OH-, you will need 2 H+ to make 2 molecules of water, right? Because each H+ will react with 1 OH- to make 1 molecule of water. And so you need 2 H+ to react with the 2 OH-, and they will make 2 molecules of water. So to do this, you have a 2 in front of HCl and a 2 in front of water. And let's look at it again. We can see that now chloride is balanced. You have 2 chloride on the left, coming from the HCl, and on the right you have 2 chlorine in the MgCl2 formula. Magnesium still 1 on both sides. If you count the hydrogens, on the left side you have 2 hydrogens from the acid, and on the base you have 2 hydrogens as well. 2 + 2 is 4 hydrogens on the left. And on the right, you have 2 times 2 hydrogens coming from water. So that's 4 hydrogens there. For oxygen, you count the oxygens coming from the base here. There is 2 oxygens in MgOH 2 times. And on the right side, there is 2 oxygens in the water coming from the 2 molecules of water. So the equation is balanced. So this is practice problem number 15 in your list of practice problems from your list of practice problems in chapter 9. It is asking you to write the balanced equation for the reaction of the following reactant. So you may want to pause the video so you can think about this and do the work before you check your answer. So first you want to identify which one is the acid, which one is the base. In the first 2 reactants there, the acid will be HNO3 because it has H as first in the formula. So that's nitric acid. Then plus NaOH, that's your base, and hopefully you recognize that there is the OH- ion in that formula. It's combined with Na+, an alkali metal of group 1A. Na sodium makes the ion Na+, and so with OH- it makes the sodium hydroxide compound. So, and HNO3 is the acid. It will donate its proton to the base, and the base here is the OH minus found in NaOH. H plus OH minus make water, right? The positive and negative charge cancel, and you have 2 hydrogens and 1 oxygen, which is water. Next, you have Na plus that is left, and NO3 minus. The NO3 minus is the nitrate ion. It has 1 negative charge. Na plus NO3 minus, they each have 1 charge, 1 positive, 1 negative charge. So one of each of these 2 ions will make a neutral formula. So the formula will be NaNO3. If you look at the equation as it is written now, you can see that it's already balanced. We have 1 Na on the left, 1 Na on the right, 1 NO3 on the left, 1 NO3 on the right. We have 1 hydrogen in nitric acid plus 1 hydrogen in sodium hydroxide. That's 2 hydrogens on the left. And on the right, we have 2 hydrogens in the molecule of water. The last thing is the oxygen in NaOH, and we'll retrieve that oxygen in water, 1 oxygen. Notice how I don't count the oxygens that are associated with the nitrate ion. These have been counted as a unit. The nitrate ion, you want to count it as one thing and do not dissociate it. So this is balanced. The next two sets of, the next set of 2 reactants here, H2SO4 plus KOH, identify the acid and the base. Again, the acid is the one with the formula starting with an H, and that's H2SO4. H2SO4 is the sulfuric acid. It's a strong acid. KOH is the base. Hopefully you recognize there is OH minus in this formula. OH minus is combined with K plus. K plus is the potassium ion, group 1A. Potassium makes a positive 1 ion. Again, the acid will react with the base by donating its proton to the base. And here we have 2 protons in H2SO4, and they will both react and leave the acid formula. And so those 2 H plus will react with OH minus and form water, H2O. We will have to balance that later on, but we can see already that we will have 2 molecules of water because of those 2 H plus, and we will need a 2 in front of KOH to have 2 OH minus to react with those 2 H plus, and together they will make 2 molecules of water. Once the acid has donated these 2 protons, what's left is the sulfate ion, SO4 negative 2. SO4 negative 2, and coming from the base, we have K plus. So we find the formula of the salt by placing the positive ion first, and then the SO4 negative 2. If you do the crisscross trick, you see that the negative 2 from the charge of the sulfate will be a subscript for K, and we will have K2SO4 because the positive charge from K is 1, and so we need only 1 sulfate. And you're looking at K2SO4, you see that it's a neutral formula because SO4 comes with 2 negative charges, and the 2K comes, they bring each a positive charge. So 2 positive charges total balance the 2 negative charges from the sulfate. And we can see that this is balanced. We have 1 SO4 on the right, 1 SO4 on the left. The sulfate ion, you do not want to dissociate that when balancing. We have 2K, 2 potassium on the left, 2K on the right in the K2SO4 formula. And finally, we have 2H plus reacting with 2OH minus, making 2 molecules of water. But if we look at the balancing, it's 2H from the acid plus 2 H's from the KOH base. That's 4 hydrogens on the left, and on the right we have 2 times 2 4 hydrogens on the right, coming from the water molecules. So this is balanced. So the second type of common acid-base reactions that we want to look at are the reactions of acid with bicarbonate base. A bicarbonate base is HCO3 negative 1. So it's an anion, so it will be typically associated with a positive ion. So most of the time it's those alkali metal or alkaline earth metals binding to the bicarbonate to make a salt. And so these, they will react with H plus, with coming from an acid, to form the carbonic acid, H2CO3. Right? You see that when you add H plus to HCO3 negative 1, the positive charge and negative charge cancel, and you have 2 hydrogens and then CO3. And H2CO3 is neutral. This is written in the form of a chemical equation here. On the left side, we have H plus HCO3 negative 1. When the H plus combines with the bicarbonate, we obtain the carbonic acid. And one thing you may already know is that the carbonic acid is not stable and decomposes into water and carbon dioxide. Maybe you remember that we talked about carbonated beverages, and carbonated beverages have carbonic acid dissolved in solution. And when you open the bottles of your carbonated beverages, you release the pressure of CO2 that is in the bottle, and this will render the CO2 less soluble in solution. And that will also mean the carbonic acid will decompose and become H2O and CO2. And CO2 is a gas and it will escape in the air. An example of that is, for example, the hydrochloric acid when you add it to the sodium bicarbonate. So the H plus from the acid will combine with the HCO3 negative 1 ion, the bicarbonate, and you will obtain H2CO3. The Na plus will combine with the Cl minus, and that's the famous stable salt, NaCl. And we know that H2CO3 is not stable and decomposes into water and carbon dioxide. This may remind you a reaction you did in one lab where you had a beaker, a plastic beaker full of hydrochloric acid, and you have dropped a tablet of antacid, a seltzer tablet, and it was made of sodium bicarbonate. And so when you drop the tablet, it made bubbles, and you produced basically a salted solution with carbonic acid. But the carbonic acid is the reason why you had bubbles, because it's not stable and it decomposed into water and CO2, and the CO2 escaped in the form of bubbles. And that's how we could see a difference in mass between the product versus the reactant, right? You took the mass of the reactant And then you took the mass after the tablet was in the solution and all the gas had escaped, the CO2. And the difference in mass between before the reaction and after the reaction was due to the CO2 that had escaped. And that allowed you to know the amount of CO2 that had escaped. Another type of reactions that we will look at is reactions of acid with the carbonate base. Here the title should be carbonate base. The carbonate base is the carbonate ion, CO3 negative 2. That's the carbonate ion, and it can react with acids and grab 2 H+ to form the carbonic acid, H2CO3. So the reaction here shows how the 2 H+ combined with the carbonate ion. And so when you put those two together, the 2 H+ become H2CO3. The 2 negative charges from the carbonate cancel the 2 positive charges from the 2 H+. And so H2CO3 is the carbonic acid, and that's a neutral molecule. Again, we know that H2CO3, the carbonic acid, is not stable and decomposes into water and CO2. Let's look at a more precise example of what this may look like. For example, if we make HCl react with sodium carbonate, Na2CO3 is sodium carbonate. Again, the 2H+ from the acid will combine with the CO3 negative 2. Together they will make the carbonic acid, H2CO3. And then the 2 Na+ that comes from this Na2CO3, right? You recognize here the sodium metal, which makes the sodium plus as ions. So those 2 Na+ combines with the 2 Cl- from the HCl. And it's 1 Na+ that is needed to cancel 1 Cl-, right? Together they make a neutral compound. So it's just NaCl, but you make two moles of them when you have 2 HCl and Na2CO3. That's how this is balanced. And again, the carbonic acid is not stable and decomposes into H2O and CO2, which escapes as a gas. And this is the end of that video.